I'll take this. Okay, thank you, Mario. Thank you for the introduction and the invitation. Thank you to everybody for coming here. Hopefully one of the last times we appeared to each other as little squares like this. And I guess I'm to go to about 1/2 past the hour. I think that will work. And you let me know if there's any problem seeing what I've got up on the screen. So what I'll talk about today is a joint work with Andrew Lopp. And I guess of the topics in this special session, probably connect most closely with surfaces. So here we go. I should say motivation. The motivation is this notorious problem posed over 100 years ago. This is the square peg problem raised by Otto Toeplitz. And what it asks is whether every continuous Jordan curve in the Euclidean plane contains 4 points at the vertices of a square. So it's an attempt to say that every, the most basic kind of topological phenomenon you might think of, a simple closed curve in the plane, has a sort of unavoidable geometry to it, a very appealing way, just 4 points at the vertices of a square. But it's an open problem, and it's a resisted solution, but in its wake given rise to a lot of interesting variations and relatives. And I'm going to talk about one of those today. So to fix the meanings of terms, I think you all know, but a Jordan curve, this is just, it's a pseudonym of a simple closed curve in the plane. And when we refer to Jordan curves without qualification, they're just assumed to be continuous maps, images of continuous maps of a circle to the plane, one-to-one continuous map, but often we'll put qualifiers in front. So these pictures are meant to depict a few examples of Jordan curves, or regions whose boundaries are Jordan curves. And what we are interested in are point sets inscribed in a Jordan curve. So I'm going to say that if I have a curve in place and I have a point set in the plane, the curve inscribes that set if there's a similarity which preserves orientation of the plane which takes P to the curve. So here we have, for 2 of our representative Jordan curves, pictures of squares, vertices of squares inscribed in the curves. And I don't care so much about how the sides of the square interact with the regions into which the curve divides the plane. I just care about finding 4 points on the curve at the vertices of a square. So that's the problem. Maybe before getting into progress on this problem, let me frame it a little bit more. You might ask why this is a natural feature to look for. Well, on the one hand, you can justify it by saying that if you're looking for 3-point configurations on curves, the problem is underdetermined. So actually, if you have any triangle and any Jordan curve, you can find an inscription of the triangle in the curve. And that's a pleasant exercise. If you look for 5-point configurations, on the other hand, the problem is overdetermined. So actually, if you take dissimilar ellipses, they don't inscribe similar pentagons, and for the reason that different ellipses can overlap in at most 4 points. So 4 is kind of the right request. And, that's, 4 is a special dimension in geometry and topology, and its appearance here is, more than just a superficial relationship to that fact. We're actually going to do some serious 4-dimensional geometry in a bit. So that frames the problem a little bit more, perhaps. And I'll talk a little bit about progress on it. So there was progress quickly made, and the one result from kind of long ago I want to mention is that Schnirelmann settled the problem if we put enough regularity onto the curve. So for smooth curves or even C2 curves, he was able to show that you can always find an inscribed square. And once you know that, it's tempting to think about the case of a continuous curve. That's because any continuous curve is a limit of smooth ones. You can prove that in many ways. So what you might do is take a sequence of smooth ones limiting to a given continuous one and take a square, which is guaranteed on each one by Schnirelmann. And by passing to a subsequence, I can find a convergent sequence of squares which limit to the desired curve. The problem, though, is that those squares could shrink out, as depicted here. And that's a serious obstacle that we don't really seem to know how to overcome. You know, in the resulting curve here, you can easily imagine a square which materializes, but to show that there's always a compensating square in the limit, nobody's been able to show. And something I'll say a little on in the talk, I think throws a little bit more, you know, just speaks to the seriousness of this issue. I mean, cyclic quadrilaterals shrink out, as we'll see, and that's an issue. So there's been a lot of other progress to do with weakening the regularity on the curve, and just one result I mentioned due to Terry Tao from a few years ago is kind of a peculiar class of curves you might never really study. What led him to this actually was in pursuit of a counterexample to the square peg problem. Didn't end up getting a counterexample, ended up verifying it for this class of curves. But that's just to suggest maybe that's what one should look for the original problem. Okay. So some related progress, in which will lead into the main result of today's talk. There's a charming argument due to Herbert Vaughan from the 70s, which shows that every continuous Jordan curve inscribes a rectangle for points on the Jordan curve at the vertices of a rectangle. And I'll describe in the proof of the main result today where Vaughan's idea is a major influence, and I'll explain where it comes into the proof of the main result today. Kind of the pivotal but subtle insight. And that sparked some progress just a couple of years ago. So Cole Hugelmeyer was then and still is now in graduate school, and he showed that every smooth Jordan curve inscribes a rectangle whose side lengths are in ratio the square root of 3. So prior to Cole, nothing beyond the case of a square was known to appear in every smooth Jordan curve. So he found for us one more type of configuration, rectangle of aspect ratio square root 3, which appears in every smooth Jordan curve. And he got a rather sharper result just a year later, showing in essence, I won't explain the meaning here, but that every smooth Jordan curve inscribes kind of a lot of rectangles, and a lot measured by their aspect ratio. And this was in the direction of a problem which asked whether in fact you can get every similarity of class of rectangle inscribed in every smooth Jordan curve. This was the so-called rectangular peg problem. It appeared in a few places, including this really nice survey by Benjamin Mochka from several years ago in the notices of the AMS. And I would point you there for some related problems. It's a very nice survey. And we got interested in Kugelmeyer's work and wondered whether we could push beyond 1/3 and show that every smooth Jordan curve inscribes every rectangle. And that was what we indeed were able to show a little more than a year ago. So I have a picture here showing here in an ellipse, you see a handful, 4 inscribed rectangles, which are suggestive of a sweep out of rectangles which inscribe in the ellipse and which pass through all aspect ratios. And we show that every Jordan curve inscribes a rectangle of any prescribed aspect ratio. So that was what we were able to do just over a year ago. And building on that, we asked, this was a question in Mochka's survey. I mean, you could ask, a rectangle is the best you can do. So you could ask, in fact, bolstered by the case of rectangles, which quadrilaterals indeed inscribe in all smooth Jordan curves. So the first place to look, if you're trying to get an answer to this question, is the case of the circle. And there's a picture of a quadrilateral inscribed in a circle. And by definition, we call a quadrilateral cyclic if it inscribes in the unit circle. Okay, so you might ask, as had been asked, is it true that every cyclic quadrilateral inscribes in every smooth Jordan curve? And that is in fact what we were able to show a few months ago. So indeed, every smooth Jordan curve inscribes every cyclic quadrilateral up to orientation preserving similarity. And so that's the result I wanted to tell you the proof of in the second half of my talk. So remarks before getting into that. It's best possible in at least a couple of senses. So one, you couldn't hope for any wider class of quadrilateral, precisely because of the case of the circle. And also, this is a really interesting note that it's not true that every cyclic quadrilateral inscribes in every continuous Jordan curve. So if you just think about the simplest continuous Jordan curves that aren't smooth, I'd argue that those are triangles. You look at which cyclic quadrilaterals inscribe in all triangles, you find the only ones that do so are isosceles trapezoids. So those are quadrilaterals which have a pair of opposite sides which are parallel and whose other two sides are not parallel but have equal length. So they look like an isosceles triangle with the top chopped off. Don't have a picture. So what's quite interesting about that is this issue of shrink out that I mentioned earlier. So you pick a cyclic quadrilateral which is not an isosceles trapezoid, and there's a triangle which avoids it. And you can approximate that triangle by smooth Jordan curves, each of which inscribes that cyclic quadrilateral. So what must be happening is that those quadrilaterals indeed shrink out to a vertex, and that there's no compensating cyclic quadrilateral in the limit. So what this means is that if you really believe in a positive answer to the original Toeplitz square peg problem, then you need to address why there's always a compensating square, which is not a feature enjoyed by more general cyclic quadrilaterals. So you have to say why squares are special amongst cyclic quadrilaterals. Of course, we know they're special, but in the context of this problem, what makes them survive? Or you look for a counterexample. Okay, So the plan then for the rest of the talk is to just walk through the proof of this result. There will be 4 steps. The first 2 steps are relatively straightforward. And then there's a bit of magic, which I'll explain, and then we'll be on our way to finishing the argument. So to get started, I first want to get a handle on the class of cyclic quadrilaterals. So to take a step back, if you're thinking about trying to find a copy of a similarity class of inscribed rectangle in a Jordan curve, the similarity class of a triangle is determined by one parameter, namely the angle, if you will, the aspect ratio, or equivalently, the angle at which the diagonals meet. So rectangles up to similarity are a one parameter family, parameterized by the angle at which the diagonals meet. Now, cyclic quadrilaterals are a 3-dimensional family, and that's what I want to parameterize. So if we have a convex quadrilateral pictured in this way, I can record a few parameters. There's the angle at which the diagonals meet, and then there are the proportions into which the diagonals cut one another. So those R's and S's are intended to represent proportions. So those diagonals are not length 1. Those are the proportions into which they cut one another. So if I have a convex quadrilateral, I can record 2 values between 0 and 1/2, which record the proportions into which the diagonals are cut, and then this angle between 0 and pi into which that's the angle at which those diagonals meet. And as it turns out, if you fix your R, your S, and your phi, there is a 2-dimensional family of convex quadrilaterals with those parameters, because you can rescale the diagonals independently of one another. But if you look up to similarity, there's a unique cyclic quadrilateral with those parameters R, S, and phi. And the fact that's true goes back to Euclid. Euclid tells you that the product of the red length is equal to the product of the blue length precisely when the quadrilateral is cyclic. And using that fact, you show that given parameters R, S, phi, up to similarity, there's a unique cyclic quadrilateral with those parameters. So going forward then, pick your favorite parameters R, S, and phi, imagine them fixed. And what we're going to do is we're going to take a Jordan curve, and we're going to prove smooth Jordan curve, and we're going to show that we can find a cyclic quadrilateral with those parameters inscribed in it. Okay, so that's the next step. So I have my fixed parameters, and I want to go on and parameterize copies of cyclic quadrilaterals of that type in my smooth Jordan curve gamma. And now for the first time, I'm thinking of gamma as a curve in the complex plane, which is useful for the perspective to come. So the pivotal idea, or a pivotal idea coming from Vaughan's work, is to really think about breaking up the cyclic quadrilateral, or in Vaughan's case, the rectangle, into its 2 diagonals. Kind of like what we were doing a couple slides ago. So what we're thinking about is taking 2 pairs of points on gamma cross gamma and asking whether those could be diagonals of a cyclic quad of the desired type. So there's a picture of what we're looking for. So you go ahead and you pick Z and W, you pick X and Y, and you ask, can they be the diagonals of a cyclic quadrilateral of this type? And it turns out that that happens exactly when a certain linear relation is obeyed. So here I didn't write them down because they're messy and it doesn't really matter. I have it in a supplemental slide at the end. But there are these 2x2 matrices, and maybe you should think of ZW as maybe a vector, actually, ZW and XY similar, vector XY. So it just boils down to a simple linear relation between ZW and X and Y, which depends on these three parameters. With this little caveat that those 4 points should all be distinct. Otherwise, you satisfy this equation, but you're just kind of looking at a degenerate copy of the cyclic quadrilateral. It's just a single point on the curve. So what I want you to think is, we're really consider all pairs of points in gamma cross gamma, or that is to say, consider all points in gamma cross gamma. And think about applying this linear transformation, R phi composed FR, to gamma cross gamma. And what's going to result is a torus, a torus in C2. And on the other hand, I can start with gamma cross gamma, and I can apply this linear transformation Fs to it. And I'm going to get another torus in C2. And what I've got are these two tori inside of C2. And what I'm saying is that the intersection points between these two tori parameterize the cyclic quads that we're trying to find in our Jordan curve, along with one degenerate cyclic quad for each point on the curve. So the next slide just writes this out. I'm just looking at the image of gamma cross gamma under these two linear transformations. They're tori in C2. And it's the intersection points between these two tori which give the inscribed cyclic quads we're after, along with these pesky degenerations. That's the point. That's how we're parameterizing inscribed cyclic quads in gamma. It says the set of intersections between a pair of tori in C2. And what we'd like to show is that this intersection is more than just the degenerate copies. So how to do that? So those were the first two steps. Those were the straightforward steps. And now the magic is to employ the perspective of symplectic geometry and to recognize that everything we've done so far can actually be cast nicely in the symplectic category. So the space that we're working inside, where our tori live, this is C2, and this is naturally a symplectic manifold. And a smooth Jordan curve in the complex plane is tautologically Lagrangian submanifold, and that leads to the fact that this product, gamma cross gamma, is a Lagrangian torus in C2. And those tori that I was intersecting, L1 and L2, I'd like to argue that those are Lagrangian tori as well. Well, in the interest of time, let me just say that, long story short, the transformations we apply to gamma cross gamma are nice enough to show that indeed L1 and L2 are Lagrangian tori. So what we've got is a kind of a Lagrangian intersection, which exactly corresponds to cyclic quadrilaterals, which we're trying to locate on gamma. If it weren't for just this pesky loop of intersection. So we address that by this curve of intersection between L1 and L2 is nice enough. And it's nice enough, you have these two tori intersecting in force space along a curve and along some other points, possibly, hopefully. So the first thing you can do is kind of to do a cut and paste along that curve of intersection. And it turns out you can do this in the symplectic category. And what will result is you cut and paste L1 and L2 and you get a new torus. It's Lagrangian and it's immersed. And the nice thing about this one single Lagrangian torus now is that the self-intersections of this torus are what parameterize the inscribed cyclic quadrilaterals we're looking for. So now our problem is to show that this immersed Lagrangian torus that we've built actually self-intersects, that it's not embedded. And the reason that's true is to do with a very basic invariant of Lagrangian submanifolds in symplectic manifolds called the Maslov class. I know I just have like a couple minutes here, but I'm nearly finished. So to describe it, you have your immersed Lagrangian L. Forget about where it came from for a moment. If you take a loop on L, you get a loop of tangent planes along L, and those are all Lagrangian planes by construction. So you get a loop of Lagrangian two planes in C2 attached to any loop on the Lagrangian, immersed Lagrangian. And I've just drawn a picture of what happens a dimension down for an immersed Lagrangian in C. You record the tangent lines, and you get an invariant of this loop. I mean, it's the winding number. And so a similar story plays out for Lagrangians in C2. It turns out that loops are determined up to homotopy by a single integer, loops of two planes by a single integer. And this lets us define an integer valued invariant associated to any homology class of loop on an immersed Lagrangian in C2. And we get this homomorphism, which is called the Maslov class. It's the cohomology class, each upper one, and that's why it gets its name. Right, so what we do is we, long story short, find for our Lagrangian torus L, we find a basis for it, for which we're able to calculate the evaluation of the Maslov class on the generators, this x and this y, and we find that it's 4 for each one, with the consequence that the so-called minimum Maslov number of this Lagrangian, this immersed Lagrangian, is 4. Every Maslov index, the Maslov index of every loop on L is a multiple of 4. It's very direct from the construction of L. However, it turns out that any embedded Lagrangian torus in C2 always contains a loop of Maslov index 2. So this is a 30-year-old result independently due to Polterovich and Viterbo. So our L does not contain a loop of Maslov index 2. Therefore, it self-intersects, and therefore we get the cyclic quadrilateral we were looking for back on gamma. Okay. So we reached into the symplectic toolkit and we pulled out this symplectic rigidity result. It was just kind of sitting around looking for an application. There it was. And that saved the day. So now just in the last 30 seconds, I'll just say kind of the moral is that the symplectic rigidity has kind of can have unexpected consequences for inscription and plane geometry problems. And thinking in those terms, then it's maybe a template for further progress. So you might, for example, pick up Machka's survey and look at the problems in there through this light, see whether there isn't some kind of symplectic apparatus that delivers the result. And conversely, maybe you have your favorite symplectic rigidity result, and you think, well, is there some kind of concrete instance of that result which translates into a cute problem, which the rigidity result then implies a solution to. So, but for the moment, all we have is really this result to talk about. Okay, so thank you very much. Hope that makes sense. And I have some bonus slides as well, but I don't intend to go through those. So I'll leave it at that and close here. Thank you very much.
Okay, thank you very much for the talk. So, is there any questions in the audience? No? Okay. Okay. Oh, thanks again for your nice talk.
My pleasure.
My pleasure. Yeah. So, I think next speaker is.
Wait, let me stop the recording so I can start it again.